All righty. Well, good evening. I'd like to thank everyone for coming out to our Berks County Amateur Astronomical Society meeting of August 2022. A couple special things have happened in our recent past. Of course, you can point at a few different scientific achievements over this past year alone, even during the calendar year 2022. And there are some incredible things happening, and we are so lucky to have some insights into what's going on. So to help us out with that, and our speaker for this evening, I'd like to give a great thank you preemptively, but also a warm welcome to Dr. Ian Wong. He is on the James Webb Space Telescope team with the exoplanet research. So I'm going to let him tell you all about it. So without further ado, Dr. Ian, take it away.
All right, thanks for that introduction. Can everybody hear me well in the room?
Yes.
Okay. So today I wanted to give sort of a very broad general overview of kind of not just JWST exoplanet science, but sort of exoplanet science as a whole. Of course, this is something that's very difficult to fit into, a 60 to 90-minute presentation, but I'll try my best to kind of give you some of the highlights. Many people in the room may not be super intimately familiar with exoplanet science, especially some of the recent developments. So so I have a kind of a general roadmap for this presentation. So kind of the first chapter will be sort of an overview of how we discover exoplanets and sort of the current status of our understanding of planet demographics throughout the galaxy. And then I'll go into sort of some of my more kind of my specialization within exoplanet science, which is studying their atmospheres, kind of summarizing and reprising some of the major highlights from the past 20 years of observations. And then at that point, I will go into some of the big open questions that JWST will hopefully answer in some way. And then finally, of course, I will give a good overview of some of the exciting science that JWST will enable in the coming years. So I think my general roadmap will probably be, I'll go through each of these chapters, and then at the end of them, I will open to some questions. I think that's a good way of going about things for this evening. So yeah, I will let you know when I'll take some questions at the end of each of these segments. Okay, so from since time immemorial, the human race has been really interested in asking questions about, are we alone? Where is our place in the universe? And before the scientific method in modern astronomy, this was primarily restricted to observations with the naked eye, looking at planets that moved across the starry night sky. So already in antiquity, we knew of many planets, and at the dawn of the 20th century, we knew 8 planets, a menagerie of smaller bodies such as comets, asteroids, and other smaller astronomical objects. So it was sort of at this time where scientists started really asking the question in earnest of whether or not there were planets orbiting around other stars. So throughout the beginning and middle of the 20th century, there were several sort of exploratory works that kind of imagined what it would take to detect analogous planets, such as those in our own solar system around other stars. But it really took many decades of technological advances in the telescope realm to really enable us to actually finally detect exoplanets. So how do we primarily detect exoplanets? So unlike with the planets in our own solar system, we can't, in most cases, directly observe the exoplanets with their own light. They're just too faint and too close to their host stars to resolve even with the most advanced modern instruments currently in service. So by and large, the methods we use to detect exoplanets are indirect. That is, we use the planet's effect on its host star's light as a way to not only infer its existence, but also to characterize its properties. So the two most productive methods so far to detect exoplanets are shown here. We have on the left transit photometry. This is when the planet passes in the front of the host star, and we see a decrease in the star's light due to the area of the star's surface that's being blocked or occulted by the planet's disk. And second method on the right is called radial velocity. This is very similar to the Doppler effect with sound, but this time with light. As the gravitational pull of the planet is jostling the host star around the common center of mass, we observe a blue and red shifting of the star's light, which can then be backed out to infer the presence of the planet. So, of course, I'll go into a little bit more detail about these individual methods in a bit. I will, of course, acknowledge that there are recent instances in which we are able to directly detect exoplanets. And this is a spectacular animation of the HR 8799 system, which has 4 planets known. And you can see them orbiting over the course of several years around its host star. The kind of disk in the middle is the host star blocked by a mask, so that we can actually directly measure the light from the planets. But these are very exceptional cases, and even with modern instrumentation, it requires very specific and special circumstances to allow for this type of observations. But of course, this will change in the coming decades with improvements in technology. All right, so let's talk about the two workhorse methods in more detail. So the transit method, as I mentioned before, it involves the planet passing in front of the star. And we can learn several things by observing transit. First of all, by observing multiple transits, we can quickly measure the orbital period, that is, the distance, the time interval between consecutive transits. And from there, in some basic stellar characterization, we can get at the orbital distance of the planet from its host star. Perhaps the most important aspect of the planet that we can infer from a transit is its radius. So the larger the planet, the more of the star's disk it occults during transit. And by measuring and fitting for this decrease in light during a transit event, we can quickly get the radius of the planet. At greater detail, we can look at the specific shape of the transit light curve to infer some more kind of special and more kind of second order types of information about the planet's orbit, namely its inclination. So inclination, as we define it in exoplanet science, is basically where along the star's disk the planet transits. So in the animation here, we see that the planets are passing along the star's equator, but this is not necessarily true. You can have grazing transits where the planet just barely dips into the star's disk. So by modeling in detail the transit light curve shape, we can infer things like the inclination as well as the orbital eccentricity. So this is the main takeaway from the transit method. So the next method is the radial velocity method. And as I mentioned before, this is analogous to the Doppler effect. So what happens is the star and the planet are mutually attacking each other, and they're orbiting across around their common center of mass. So because we can't observe the planet's light directly, we instead use the reflex motion of the star to infer the planet's presence. So as a star is moving around the common center of mass, it is periodically blue shifted and red shifted. And with very precise spectrometers, we're able to detect extremely small velocities in the star, down to below 1 meter per second. This is kind of an astounding value. You're thinking about a star that is tens of light years away potentially, but we can essentially measure a walking speed of the star's entire surface using this method. And this sort of goes to show you how much the technology of telescopes plays a big role in enabling this type of exoplanet science. So from the radial velocity method, we're able to get the mass of the planet. The more massive the planet is, the more it tugs on the star, and the bigger the signal in radial velocities. Likewise, we also get the orbital period as well as some picture of the orbital configuration from this RV method. So actually the most productive way, the most powerful way of characterizing, at least the first order, characterizing exoplanets is to combine these two methods. If you have a system that is both transiting and showing radial velocities, you get both the mass and the radius of the planet. And together, that allows you to characterize the planet via its density, whether it has an atmosphere, whether it's more a rocky planet. Those instances are perhaps the most valuable because it gives you a full picture of the planet's properties. So on the right here, I show a very, very famous plot in the exoplanet community. This is the discovery radial velocity curve of 51 Pegasi b. And this is the first exoplanet discovered around a sun-like star. And this is unfortunately not a transiting system. So the system doesn't transit, but nevertheless, we have a very strong radial velocity signal that from which we can infer that this planet has a gas giant composition. It's a massive planet, somewhat like Jupiter. And this was a 1995 discovery and was recently awarded the Nobel Prize in Physics. All right, so how do what facilities do we use to discover exoplanets? So early on, most of the discoveries were carried out using ground-based instruments, primarily using the radial velocity method. But starting in the mid-2000s, there were a series of space-based surveys that were specifically designed to probe transits. The first one's Corot, but perhaps the most famous one is Kepler, which had almost a decade-long campaign that discovered thousands of transiting exoplanets. And they did this in a very systematic way that not only yielded a sort of a watershed of thousands of exoplanets, but it allowed us to do very, very detailed statistics to characterize the demographics of exoplanets throughout the galaxy. Recently, in 2018, the successor instrument TESS was launched, and this is a sort of a co-PI'd mission with MIT and NASA, and it is ongoing, and it has also yielded thousands of transiting exoplanets, primarily around brighter stars. And why are brighter stars important? Brighter stars are easier to follow up with ground-based instruments. And brighter stars also enable very detailed atmospheric characterization, which is one of the main objectives of JWST, as we'll go into in a little more detail later. So sort of the landscape of exoplanet discoveries looks like this. So here's a plot of the cumulative number of detections per year, starting from the early 1990s to 2021. This is a little bit out of date, but you get the sense of this exponential explosion around between 2010 and 2015. And this is truly the effect of Kepler. So in green, we have the transits. So these are planets that are discovered using the transit method. And in red, more steady increase from the radial velocities from the ground. And as of mid-2021, we have over 5,000 confirmed exoplanets, with thousands of other candidates that are known and soon to be probably confirmed. So what is our current picture of exoplanet demographics? So this plot on the bottom right is something that a lot of exoplanet presenters kind of slap on slides. It's kind of a very classic plot. So you have on the x-axis orbital period in days. And then on the y-axis, you have masses, the mass of the planet in units of Earth mass. And you have in red the solar system planets labeled. And all the other colors, all the other dots are exoplanets that are discovered. Now, there are sort of three major clumps that you can pick out here by eye. Starting at the upper right, you have a clump of cool gas giants. So these are gas giants that are on sort of year-long orbits. So they are comparable to Jupiter and Saturn in our own solar system. And these are almost exclusively discovered using the radial velocity method. The chances of these objects transiting in front of the star and then us capturing it in transit is minuscule. So these are all radial velocity detections. Now, the second clump over in the upper left is perhaps the most productive subset, the most powerful subset of exoplanets from the vantage point of atmospheric characterization. And these are the hot Jupiters. So these are gas giant planets with masses in excess of 8 to 10 Earth masses but they orbit very, very close to their host stars, sometimes on orbital periods less than a day. So they are extremely hot, hence their name. They're bright, and they're also extremely amenable to atmospheric characterization by virtue of not only their short periods, but their intrinsic brightness, their hotness. So these are predominantly discovered using the transit method. Kepler ground-based surveys and tests have yielded thousands of these, and they continue to be some of the most promising candidates for detailed study. Now, if you move down to the bottom left of this plot, you have what is essentially two distinct populations. They're related in a way that is not fully understood yet, but these are planets that are not really seen in our solar system. They have masses that are comparable to Earth or somewhere between Earth and Neptune, but they are much hotter. They lie on very short orbit, tens of days in many cases. So they are completely not tested in our own solar system. Now we have at the lower end of the mass distribution, super Earths. So these are Earth-like planets, so terrestrial planets, rocky, high-density planets, but much closer to their host stars, so very hot. Oftentimes they're lava worlds with surfaces that we think are covered in molten rock. And then just above that, we have another very interesting subclass of exoplanet called warm Neptunes or sub-Neptunes. These are planets that are just a little bit more massive than the super Earths, but clearly show evidence of at least a partial atmosphere. So they have densities that are very similar to the ice giants, Uranus and Neptune, in our own solar system, but they're much hotter. And the distribution of warm Neptunes and super Earth is one of the most important open questions currently in exoplanet science. And it informs sort of very fundamental questions of how exoplanets form in general. So to look at this in more detail, here's a planet frequency plot. So on the x-axis, we have planetary radius in this case, not mass. And on the y-axis, we have the number of planets per star with an orbital period of less than 100 days. It's kind of a little bit weird criteria, but bear with me. This will become clear in a second. So basically, this is mostly driven by detections from the Kepler survey. Now, in black, you have the curve of planet frequency bin in log scale. And you can see that by and large, planets are small. So around most stars, you're expecting to find small planets, more likely to find small planets than large planets. So these vertical bars correspond, the colored vertical bars correspond to the planets shown in our own solar system. You see that you have this huge peak of exoplanet frequency in between Earth and Neptune, as far as radius is concerned. And these correspond to the super Earths and the sub-Neptunes. But what's more interesting is that it's not a smooth distribution. There are clearly these two peaks there with a little bit of a gap in the middle. And this is how we distinguish between super Earth and the hot sub-Neptunes. And this gap is very, very peculiar. You would maybe naively expect that there would be a smooth distribution in the radius or mass of planets. But clearly, the physics of planet formation makes this not the case. So there are many potential explanations for this gap, some of which I'll get into later. But that's sort of one of the most interesting aspects of our current understanding of exoplanet demographics. So here are some, on the bottom, you have some sort of trivia facts that are pretty astounding. If we look at the statistics from the Kepler mission and extrapolate it and correct for biases, we find that on average, every single star in the galaxy is expected to have at least one planet around it. So this is really astounding. So if you look out in the night sky, point to any star, on average, there is one planet there. So planets are ubiquitous. They are a natural product of star formation. And the exoplanets are basically a common feature everywhere in the galaxy. Going one step further in specificity, if you look at sun-like stars alone, we find that 1 in 5 on average has an Earth-sized planet within the habitable zone. So habitable zone, loosely defined, is a zone around the host star where liquid water can survive in equilibrium on the surface. So Earth and Venus in our solar system lie in the habitable zone of our sun. So if we kind of extend that definition to different types of stars, we can define a habitable zone around each host star. So 20% of sun-like stars have a potentially habitable Earth-sized planet, which is really a very shocking finding. So in addition to just the ubiquity of exoplanets in general, habitable zone planets are also very, very common. So this, of course, leads into the questions of potential habitability, basic and complex life, some of the more metaphysical questions about exoplanets and our place in the universe. All right, so at this point, I wanted to take a quick break for questions from the room.
So you have a bimodal graph there. You're saying that planets around other stars are likely to be a little bit larger than Earth's radius and a little bit smaller than Neptune's radius?
Yeah, so the predominant type of planet is one that has a mass and radius that is somewhat intermediate between the rocky planets in our solar system and the ice giants. So somewhere in between is the sort of Goldilocks zone for planet formation.
And a planet like Jupiter or Saturn is more unlikely, or I'd say, less observed. So,
I want to make sure I reiterate that this is a sort of a de-biased frequency. So if you look at the previous plot, numerically, as far as the known planets are concerned, we have lots of gas giants. But that is mostly a function of the ease with which we can detect them. They're more massive, so the radial velocity signal is larger. So it's easier to detect their radial velocity signal. Likewise, they occult more of their star's light during transit, so they are more likely to be above the sensitivity level of a given instrument. So these are all things that have to be de-biased when you convert this little two-dimensional plot on this slide to this normalized frequency on this slide. So even though we know of many hundreds, actually thousands of gas giant exoplanets, something like 30% of all the known exoplanets are gas giants. If you account for these biases in detection, it actually turns out that smaller planets are very more frequent, but they're of course harder to detect. So we know relatively fewer of them, but they are intrinsically more frequent in the universe.
I have a question. Can you hear me?
Yes.
You mentioned some of the Jupiter-sized planets that detected have an average velocity, an average orbital period around their star of less than a day.
Yes.
Is that correct?
Yes.
In your opinion, would the tidal forces on that planet be so large that the demise of the planet would be quick and would be short-lived because of the forces? And is it at the end of its life before the star absorbs it?
Yeah, so this is a great question. So we do know of many cases where we can observe the tidal effects of the star on the planet. These are sort of very distended gas giants, oftentimes with escaping atmosphere. So certainly if you were to turn the clock forward, give a few tens of millions of years, that atmosphere will be stripped away. And then also, the tidal forces can actually shorten the orbital period over time. So essentially, you're pulling in the gas giant into the star. And we think that actually is a feature of planet formation. The planets that you see in the present day are only a fraction of what may have initially formed. But through either dynamical or other reasons, some of these planets can be lost. And one very efficient way of destroying planets is to suck them into the star. And numerical models readily show that in the early, first million or so years, few million years of a source of an exoplanet system, you can have several gas giants worth of mass disappear into the star. And this can happen very rapidly. Yeah, so certainly there is an inner limit to which gas giant's orbit is stable. And we can clearly define that from the fundamental properties of the star. And we actually see gas giants all the way up to that limit. So they kind of pile up at that limit. So we know that certainly there were in the past some planets that must have fallen into that kind of no-go zone and were quickly sucked up by the star. So yeah, so definitely tidal forces are really destructive force for these hot Jupiters.
Okay, just one more question. With today's technology, not counting the James Webb, if we were in your opinion, if we were on 51 Pegasi, could we detect the 4 gas giants around our star?
So with our current technology, it is difficult, but probably possible. And it's contingent on a lot of things. So if you were, so Jupiter has a long orbit, about 9.6 years, give or take. So you would have to observe for a significant fraction of that regularly to get its radial velocity signal, for example. Likewise, the transit happens once per period. So you'd have to be extremely lucky to look at the star at the right time to see the transit. So as I mentioned with the demographics plot, usually most of these distant planets, Jupiter, Saturn, are like planets. They are detected using the radial velocity. But even then, objects on 10-year orbits are very difficult to detect and require sort of the cutting-edge instruments that we have. But the peak-to-peak amplitude of the RV signal for Jupiter is easy to get with modern technology. Likewise with Saturn, current radial velocity instruments can readily detect that amplitude. The question is just the stability of the instrument across 5 to 10 years. Yeah.
Thank you.
All right. Any more questions?
I think we're good.
All right. So moving on to the second part of my presentation is going to be a kind of a deep dive, maybe not so deep, but a brief perusal of some of the highlights of exoplanet atmosphere. So discovering exoplanets is one thing. You know their distribution, their demographics, their size, and their mass. But what we really want to know is their properties, kind of really get to know their personality, so to speak. So every planet is different. There's different gases in its atmosphere. The temperatures are different. The atmospheric dynamics can differ in many substantial ways. So there's a whole arsenal of tools, observational tools, that we can use to infer various properties of an exoplanet's atmosphere. So by and large, exoplanet atmospheric characterization hitherto has been limited to gas giants. Gas giants in sort of large Neptune-sized exoplanets, but this will change with JWST. So here's some of the kind of big overarching themes that we are interested in when we talk about exoplanet atmospheres. So first of all, we want to know what kind of gases be found in the atmosphere. So some of the most common gases in the universe, water vapor, methane, carbon dioxide, have been detected on dozens of exoplanets hitherto. But sort of through finer detail, there's some more trace species that can be very, very influential on the atmospheric dynamics. You have these exotic species like titanium oxide, which are often at parts per billion abundances in the stratospheres of exoplanets, but they have an outsized role in controlling the next topic, which is temperature structure. So Earth's temperature structure is highly nonlinear. You see here the plot here shows Earth's temperature pressure profile. So it cools down in the troposphere, but then it turns around, it inverts through the stratosphere, and then it has several other inflection points before you get into to outer space. So we have characterized the temperature structures of many gas giants in ever increasing detail. And the interplay between composition and temperature structure is one of the leading open questions about large-scale atmospheric properties in gas giants. In the upper right, we have convection and mixing. Atmospheres are static objects. They are extremely dynamic, extremely boisterous. The animation on the bottom left of Jupiter's atmosphere is a good example. You have bands, they're moving at different velocities. You have storms, some of which are extremely persistent. And also in the vertical direction, you can have convection. Warm air being heated is lofted up to higher altitudes and then cools down and sinks back down. So we see this on Earth, drives sort of the fundamental storm patterns in the tropics, for example. But on exoplanets, we also see evidence for this vertical mixing of different atmospheric layers. Clouds are also a very ubiquitous feature of gas giant atmospheres. The majority of the overwhelming majority of gas giants that have been characterized show evidence for significant cloud cover, and clouds can be very exotic on exoplanets. Here on Earth, we have water clouds, but at higher temperatures, you actually have, for example, molten or vaporized rock being the primary condensing species that you see in these clouds. So you have these very kind of alien molten rock, molten metals lofted into the atmosphere and condensing to form out by structures that have many of the same properties as water clouds do, storm clouds do on Earth. You can have precipitation, raining iron, raining rocks on these hot Jupiters. And lastly, we have photochemistry. So photochemistry is the interaction between the star's light and the upper layers of the planet's atmosphere. And there's some complex chemistry that can go on wherein some of the more fundamental molecules of water and carbon dioxide are processed and reconfigured into more complex hydrocarbons. This is analogous to hazes and smogs on Earth, which are driven in part by the interaction between sunlight and the organic molecules. And we have also observed hazes and hints of photochemistry on many gas giant atmospheres. So, atmospheres of exoplanets. So there are several methods. The first method, which is probably the most popular in recent years, is called transmission spectroscopy. So as the name suggests, we are looking at the starlight being transmitted through the upper atmosphere of the planet. So I like to make the analogy that essentially what we're doing is we're seeing the sunrise and sunset of the entire limb of the planet simultaneously. So all the sunsets and sunrises are being observed at the same time. So at the edge of the planet, the transmitted starlight interacts with the molecules in the atmosphere, and through this process, it can imprint some kind of fingerprints of the composition into the spectrum that you measure. The second method is similar, but it is observing the planet when it passes behind a star. So when the planet passes behind a star, the total dayside brightness disappears, and you can invert that to get the thermal emission and reflected starlight components from the atmosphere. And this gives you a different view of the atmosphere. Instead of looking at the upper limb of the atmosphere during transmission, you're seeing the entire dayside, the hemisphere facing the star at once. And that gives you information about the temperature in the dayside, the temperature pressure profile, and presence or absence of clouds. The last method, perhaps the most intensive, is phase curve photometry or spectroscopy. So phase curve in the exoplanet field means the total orbital variation in the planet's brightness as it orbits around the star. So across an entire orbit, you measure the total brightness, the star and the planet. And once you subtract the star's light, you get the brightness of the planet as a function of its orbital phase. Now, this is particularly useful for hot Jupiters because of its proximity to its host star, the tidal forces are such that the same hemisphere of the planet is locked in the same configuration relative to the stars. So you have tidal locking, and you have a constant day side that is always facing the stars, the star, and then you have a colder night side that is never seeing any direct sunlight. So as the planet is orbiting around its star, we can observe every longitude of its atmosphere and then back out a brightness map in 2D, usually, well, 1D or 2D of the planet, which is an extremely powerful tool for understanding sort of global thermal budgets, winds and temperature structures. All right, so the next slide gives a little bit more of an illustrative view of what's going on in these three techniques. So transmission spectroscopy, as I mentioned before, you're seeing the very upper limb, the very upper layers of the planet's limb as it passes in front of its star. Any molecules that are in the starlight's path can absorb some fraction of the starlight, leaving behind the telltale signs of its molecular composition. In mission spectroscopy, we are seeing the entire planet's hemisphere, day-side hemisphere, disappearing behind the host star during the eclipse. And with phase curves, this is an actual data set that was observed for a hot Jupiter. We can actually constrain global weather maps of exoplanets using the phase curve method. Phase curve methods are basically the catch-all. It includes everything about the planet, both the transits and the eclipse, and everything in between. So in addition to the techniques we use, we also have different wavelengths that we can focus on. And the characteristic types of science that we can do at a particular wavelength can differ very much. So, here we have an EM spectrum, the electromagnetic spectrum. The visible light is useful for things like looking at clouds. Just like on Earth, clouds are, at least partially opaque. And likewise, on exoplanets, if you look at visible spectra, we can see the effects of clouds attenuating the star's light in transmission. If you look at the ultraviolet, we have very strong features due to hazes. These are fine particles like soots, or analogous to smog on Earth, and they interact in a very characteristic way with the starlight and can imprint their features into the spectrum that we measure. Now, the infrared is a particularly interesting region of wavelength space, and indeed, JWST is very much focused on the infrared. So why is infrared very important? Is it's home to some of the most important and most characteristic absorption features for gases such as water, carbon dioxide, methane. All these extremely prevalent gases have their major absorption features in the near infrared. As you go farther into the mid-infrared, you're actually looking at the heat, the thermal spectrum of the planet, and you can measure in great detail the temperature distribution, as well as other features such as clouds and other things like that. So the infrared has is very dense in information content, and that is exactly why all the kind of recent instruments, JWST, and of course near future instruments also, they're focused very much on the infrared. So what does a transmission spectrum look like? So here is this is kind of a weird noodly plot. You have all these colored curves. These are the opacities of different major atmospheric species. You have dark blue water, but you also have things like ammonia, atomic sodium, CO2. These are all extremely prevalent gases and atmospheric components on a galactic scale, and they each have a very, very specific fingerprint in their spectra. So on the x-axis, we have wavelength going from sort of the red optical region to almost the mid-infrared. And the y-axis, the units are not important, but it more or less gives you how absorbent this species is at that particular wavelength. The higher the curve, the more absorbing, the more light it absorbs at that wavelength. So you can see very clearly that every molecule has a very distinct pattern in its absorption. And by measuring a transmission spectrum or an emission spectrum, we can look for these telltale absorption features, these configurations within the spectrum to then infer both the presence and the abundance of a particular atmospheric species. So the analogy with the fingerprint is I think, very apropos. We're basically doing some forensics on the exoplanet atmosphere and looking for these, the loops and swirls, so to speak, of different gases. So this is model data. This is not actual real data. So let's look at some real data. So this is a paper that was recently accepted that I led, looking at the gas giant WST-80b. So here's a transmission spectrum using data for both Hubble and Spitzer. And you can see some notable features. So first of all, in the optical on the left side, we see this more or less, decreasing trend in the transit depth. And this is the telltale sign of what we call Rayleigh scattering. And this is the same reason why the sky on Earth is blue. You have the atmosphere preferentially scattering away short wavelength blue light and letting other longer wavelengths pass through more easily. And this type of downward slope is seen in many, many gas giants. And it's due to this fine particulate matter in the atmosphere that is causing Rayleigh scattering. So on this planet, if you were to take the airplane, fly around the atmosphere and look up, you would see a blue sky. That's what this means. Now, moving on into near infrared, right in the middle of this plot, okay, I can use my mouse here. There we go. Here. In the middle of this plot, we actually find this very notable feature due to water vapor. So at 1.4 microns, there's a very strong absorption due to water vapor. And this is what we're seeing here in the Hubble data, with the presence of significant water vapor in the upper atmosphere. Now, moving to redder wavelengths and really farther into the near infrared, we don't actually have a lot of instruments currently, besides JWST, we don't have a lot of instruments that can observe this wavelength range. But we do find some very interesting features that we will then be able to study with JWST. But in the absence of JWST, what we relied on is Spitzer. Spitzer is not a spectrometer, but a photometer. It does photometry in the near infrared. So we have two transit depths here at 3.6 and 4.5 microns. And the fact that the 4.5 micron point is so high indicates the presence of carbon monoxide or carbon dioxide. And so this huge ramp up in the transit depth or the transmission spectrum is the telltale sign of this CO or CO2 in the atmosphere. So this is sort of the state of the art prior to JWST, using Hubble and Spitzer together to characterize the, at relatively low resolution, characterizing the transmission spectrum of a gas giant from the blue optical all the way to something like 5 microns. So already with this admittedly pretty scant data set, we have done a lot of science. And we found molecules galore. In addition to some of the more common ones, there are these exotic vaporized silicates, vaporized rock. We have atomic metals in the hottest exoplanets. We see clouds made of silicates, clouds made basically out of the type of rock you find in the mantle of the Earth, but it's instead in the atmosphere of a gas giant and undergoing the same type of hydrological cycle, but a silicate cycle where it rains down on the night side when it's colder and then re-vaporizes on the day side when it's hot. This is very exotic, very unfamiliar types of worlds here. We have complex photochemistry, not just Rayleigh scattering, but we have complex organics being formed in the upper atmosphere due to the UV irradiation from the host star. And there's also a related kind of cycling with these soot particles. They form in the upper atmospheres to get really heavy and then they sink down. And by sinking down, they're also carrying with them not only mass, but affecting the temperature structure. So despite being very small and not very abundant, these particles can have an outsized role in controlling the temperature structure in the vertical direction and in the horizontal direction across gas giant atmospheres. And then looking at smaller planets, which before JWST we were just starting to be able to do with Hubble, we have found some very, very almost sci-fi-like worlds. We have a lot of worlds where super Earths are extremely hot on the day side, such that their entire crust is molten. We also have evidence of water worlds that are predominantly covered with a very, very thick ocean of water. So nothing like the Earth, where you have just a tiny film of water. You can have oceans extending, 10%, 20% through the radius of a super Earth. So those are some of kind of the interesting objects that are going to be studied in more detail with James Webb. Other more exotic things, we have detailed vertical temperature structures. So like the Earth, we have detected stratospheres in several gas giants. We have these inverted thermal inversions that are caused by various absorbing atmospheric species. And this is primarily determined using emission spectroscopy, looking at the eclipse of the planet at various wavelengths as it passes behind the host star. For some of the brightest and most amenable systems, we have gone even further to actually infer two-dimensional and even three-dimensional global weather patterns. And so here on the upper right, this is actually an atmospheric model, but with more data in higher precision, we were able to resolve these sort of inhomogeneities, both in longitude and latitude, in the temperature distribution. And we find that predominantly these gas giants show super rotating winds along the equator. These are winds that are rotating much faster than the planet is rotating itself. So it's transporting the hot gases from the day side to the night side. And the amount of thermal energy that's being transported is a function, very complicated function of various aspects of the planet. And this is something that we're still not fully knowledgeable about and will need more study. And lastly, before I end the section, we have escaping atmospheres. I brought this up in response to audience question, but indeed we see a lot of these close-in gas giants having their atmospheres stripped away, both by the tidal forces and also by the intense radiation of the star itself that's actually burning away the upper levels of the atmosphere. So this is the planet's GJ436. It's actually a super Neptune or kind of Neptune-sized planet. In the ultraviolet, we were able to see a very, very strange transit state that is diagnostic of this planetary tail of gases being stripped away from the planet itself. And the planet itself is very small in this plot. You have this huge cloud of escaping gas that's clearly visible in the transit. All right, so at this point, I would like to again open to questions from the audience.
So, have you seen any data from James Webb yet?
Yes. The lights in my room just turned off. What's that? All right, there we go. Yeah, in my office, I have these motion sensing lights. Yeah, so James Webb released early release observations on July 12th. One of those was an exoplanet transmission spectrum. I'll show it later in a later slide. But yeah, in addition to that, there's also data from not just early release data, but actual cycle 1 data has already been taken for many exoplanets and all other systems too, solar system, galaxies, stars. So the volume of data is immense. There's hundreds of gigs already downlinked for various programs. So it's really a deluge of data volume that's landing in our lap. So almost too much data, almost too much of a good thing. Yeah. All right, any other questions?
I think we're good.
All right, so I see that I'm running a little bit late, so I'm going to kind of breeze through a little bit more quickly the next few slides. So basically, what are some of the big sort of landmark questions that are facing us as a community as we look at the era of JWST. So, of course, we want to always look for more sensitivity. The more sensitivity we have, the more incisive our conclusions can be about a given exoplanet. So looking at exoplanet atmospheres in ever increasing detail is a high priority and one of the major objectives of James Webb. Looking more broadly, as we get more and more systems analyzed in detail, we can start thinking about bigger trends. You know, are there sort of interesting covariances between, say, the cloudiness of a Jupiter-like planet with, you know, the star's type or the temperature of the atmosphere? So these questions can only be answered as we get a larger volume of exoplanets with detailed atmospheric information. Even more broadly, this time in time, is looking at exoplanets at various stages of their lives and then extrapolating fundamental aspects of exoplanet formation evolution in general. So how do these exoplanets form? Are there different pathways that different types of exoplanets take to achieve their final form? And how do exoplanets evolve as the star evolves? So we can look at early stage planets on young stars, around young stars. You can see mature planets. And more recently, there are some exotic planets around late dead stars, like white dwarfs, that are also interesting in their own right. And lastly, and kind of closest to us as a species, is what are Earth-like planets in the galaxy like? No, is a water-rich atmosphere a common thing? Oxygen-rich atmosphere common? Or are we kind of a rare instance of a habitable bubble in the galactic sense? So all these questions will be answered, well, at least partially, by JWST. So, oops, my mouse just deactivated. Okay, there we go. So JWST was launched on Christmas morning, 2021, from the European Space Agency's launch site in Kourou, French Guiana, aboard the Ariane 5 rocket. I actually watched the live stream of this launch, and many of you in this room probably did. It was a huge life-changing experience, seeing the culmination of truly decades of work translated to a successful launch, and it actually exceeded expectations. The orbital insertion was very precise. Everything went exactly as planned. So skipping forward a bit, let's just compare Webb and Hubble. So Hubble was sort of the instrument that I grew up with. You know, it was launched the year I was born, and I saw a lot of the early science, you know, in science classes. But James Webb is a whole different beast. Hubble's primary mirror has a diameter of 2.4 meters. Webb's primary mirror is almost 3 times larger. It's so large that it had to be folded up. So he has this very unique design with these 18 hexagonal segments that had to be configured and constructed when it got to its parking orbit. This is a very unique, never before done thing in the realm of space telescopes. So the fact that it went off without a hitch is a spectacular demonstration of this technique. So where is James Webb now? So James Webb is orbiting around what we call the Lagrangian point number 2. So the Lagrangian point is a very special point in space relative to the Earth's position, where the combined gravity of the Sun and Earth is such that an object placed there will rotate or orbit the Sun at exactly the same angular rate as the Earth. So by putting Webb there, it is far away enough from the Earth that the Earth is not blocking or interfering with its instruments, but it is in a stable configuration such that it is always approximately the same distance away from Earth. So it's never drifting away from Earth or on the opposite side of the Sun from Earth. It is always at that relative position. And that was really important to enable all sorts of science. Hubble was not placed at the L2 point. It was on the low Earth orbit. It orbited the Earth. Well, I'm using past tense. It's still very much alive. Hubble orbits the Earth every 90 minutes or so. And the downside of that is if you're looking at a star near the galactic or the ecliptic, anywhere near the ecliptic, really, the Earth will block the telescope's view of it every 45 minutes or so. So almost half of Hubble's orbits will be a dead time, which can be used for observing that source. So James Webb Space Telescope avoids this by being away from the Earth, always facing away from the sun. So it's constantly being able to observe, the night sky. So what kind of instruments does James Webb have? So there's 4 science instruments on board. 3 of them are focused on the near infrared wavelength range between approximately 1 micron and 5 microns. So you have NIRSpec, which is the workhorse spectrometer, offering low to high resolution spectroscopy of both single sources and multiple sources simultaneously. You have at the bottom here NIRCam, which is the photometric counterpart to NIRSpec, is a camera that images the sky in the near infrared wavelength range. And this is useful in the exoplanet field for direct imaging, which I'll talk about in a little bit. NIRS is actually kind of a hybrid instrument. It does both imaging and spectroscopy, and it's particularly useful for very bright stars that you need to observe very rapidly. So, for example, getting a transit light curve, you need to observe at high cadence. So every, the adjacent exposures have to be pretty close to each other, and you need something that has a lot of throughput. So NIRS is that instrument that really enables extremely precise, high fidelity transmission spectroscopy for exoplanets. Looking farther into the infrared, we have the single mid-infrared instrument. This is the mid-infrared instrument called NIRI. This has both imaging and spectroscopic modes from 5 microns to 30 microns. Now, as a point of comparison, at the bottom here, I've marked the wavelength range that Hubble covers. The Hubble covered from the near ultraviolet through the visible, and then into the infrared about to 2 microns. And that was it. So James Webb really can be seen as a complementary instrument to Hubble. And the visible is not part of the wheelhouse for James Webb, very much focused on the near infrared exclusively. And this mid-infrared capability is unique to James Webb. Never have we sent a high fidelity spectrograph, powerful spectrograph into space that can cover this region down to 30 microns. So many of you have already seen these images. These are a selection from the early release observations from July 12th. So the upper left, we have the Carina Nebula, and this is the planetary nebula that really highlights the immense improvements that James Webb offers relative to Hubble. You have the side-by-side comparison of the exact same view, exact same zoom, but you can just see just how much more exquisite the fine details are in the James Webb images. Of course, exoplanets are not the only type of planets that James Webb is focused on. The solar system science is going to be addressed in a big way with James Webb. And here you have an early release image of Jupiter with Europa in the bottom left. You can see all the fine details of the banded structures, the gray red spot, all the details that this looks almost like a Voyager image, which was taken very close to the planet, but instead this is from James Webb. And so this is a very exciting image for solar system science. And there's another sample of Stephan's quintet. These are 5 galaxies, not all of them associated with each other gravitationally, but just a pretty image. These are nice pictures for the public. But of course, people are doing science on these images in a bona fide science also. So the highlight for me was this early release observation. Now, of course, this is not an image. This is a transmission spectrum of the gas giant planet WASP 96b. Now, this is a planet that's about half the mass of Jupiter, but significantly more larger in radius. So it's a very low density puffy gas giant. And we can see, if you remember the plot I showed from my paper, that only had a few points in the near infrared. Now you have the entire region from basically 0.7 to 2.8 microns covered continuously. And you can see all the water bands featured here. You have not just the 1.4 micron water band that you could see with Hubble, but you have the one at 1.8, as well as the smaller absorptions, at least hints of the smaller absorptions at lower wavelengths. So with this type of data, we can go beyond just saying, is there or is not water? We can actually start asking how much water and what the distribution of water is as a function of height in the atmosphere. And this is something that you cannot even imagine doing with Hubble, but James Webb will be able to do for dozens of systems in the coming years. So before James Webb launched, the exoplanet community was already jumping on sort of dreams of what James Webb might enable. So these are model observations of James Webb's performance for 2 different gas giants. And you can just see all these little, as I mentioned before, fingerprints, these fingerprint features of water, carbon dioxide, ammonia, being really, really faithfully traced out by the thanks to the sensitivity of the instrument. And I have this little black bar here in the middle of the upper plot. And this is what the equivalent precision of Hubble is at that wavelength. And you can just see the immense improvement in sensitivity that James Webb will offer. So James Webb will really enable us to resolve molecular abundances, elemental abundances across different regions of an exoplanet atmosphere, and also enable very, very incisive comparative planetology, comparing different types of gas giants, comparing gas giants with ice giant-like planets, and really getting at some of the more fundamental questions about planet formation and evolution. So clouds are also important. Now, clouds traditionally have been a kind of a confounding factor for exoplanet observations. They tend to attenuate a lot of the molecular features. The clouds themselves are an interesting scientific subject in and of itself. Different compositions of clouds have different molecular features. And of course, the distribution is very important for determining the thermal balance across different longitudes. So here's a sample of atmospheric models at different temperatures with different types of clouds. And you can see not only the different colors, these are actually real colors, by the way. These are optical colors, what you would see in optical. And then you also have colors that are different. You can see the different distributions. You can see the different colors. And all of this information is also captured when you look at transmission and emission spectroscopy. So detailed eclipse and transit observations from James Webb will not only enable us to detect the presence or absence of different cloud species, but we can actually map the distribution in 2-dimensional space of the cloud deck. And this is something that has extremely large implications for global atmospheric dynamics and chemistry. Yeah, so truly we're going to be seeing atmospheres in 3D. This is a model of a brown dwarf. A brown dwarf is something a little bit bigger than a gas giant. It's in between a star and a planet. There are many brown dwarfs that will be observed in the first year of James Webb. And they're nice because they're big and they're bright in the infrared. So we can actually see the different banded structures as they rotate in and out. So you can see, this kind of looks to first order like Jupiter. And indeed, with James Webb, with both the NIRSPEC and NIRI instruments, we'll be able to see in detail these atmospheric bands. And this will also really contribute to our understanding of planetary atmospheres in 3 dimensions. So skipping ahead a little bit to what I think a lot of people find to be the most exciting early science outcome of James Webb is this system. This is the TRAPPIST-1 system. It is basically the poster child for a multi-planet system of terrestrial exoplanets. So to date, we have 7 rocky planets that are known, all of which orbit closer to its host star than Mercury orbits our sun. It is around an M dwarf, a very cold star. So the habitable zone is much closer to the star than it is for the sun. And indeed, 3 of these 7 planets orbit within the broadly defined habitable zone. And so far, already 3 transits of 2 different planets within the system have been observed by James Webb in the last 20 days. So there's many of these planets will be studied in great detail, and we will be able to know whether these are indeed habitable planets. We will be able to detect water. We will be able to see if there's evidence for oceans on the surface, stable liquid ocean, and also other things like whether there's oxygen or carbon dioxide in the atmospheres, and how thick the atmospheres are. So James Webb will, for the first time, allow us to peer into the atmospheres of smaller sized planets, planets more like our own. And this will kind of broaden the scientific output beyond the traditional gas giants, hot Jupiters, to all sorts of different types of planets. So to me, this is probably the most exciting part. We will be able to look at the whole diversity of known exoplanets in great detail for the first time. So with that, I'll end and I'll take questions from the audience for the whole presentation. So thank you for your attention.
I have a question. Why was the telescope launched from Guyana instead of Florida?
Well, so the main sort of logistical reason is it's a European, the rocket is European. It's an Ariane rocket. So it has to use the European facilities. But why would it be in Guyana and not in Europe, for example, is just due to the dynamics. We would always want to launch as close to the equator as possible, because the linear velocity of the surface is the highest there. So you get more oomph just from Earth's rotation by being close to the equator. That's why Cape Canaveral is as close to the equator as possible for continental US, and a lot of the major other launch facilities are near the equator. Yeah.
Do you have any objects that you are looking forward to studying, and how far planned out are they?
Yeah, so in the first year, I think one of the I showed this this plot from a paper I had published just last month. This is WST 80. It's a gas giant, and this will actually be observed during the first year of James Webb as a this is a guaranteed time. So this is actually selected by the science team prior to launch as a high priority target that was guaranteed to be scheduled during the first year. So this was not a proposed for by the community. The science team determined that this was important enough of an object to include to showcase the abilities of the spacecraft. So we will get both near-infrared, both eclipse and transit spectroscopy of this target in the first year. So I'm really excited to see this whole wavelength range filled in with high sea-level noise points, and we will be able to look at exactly how much water is there. Is it CO or CO2 that is responsible for that feature at 4 microns? We don't know. With the data we have now with Spitzer, we can't tell because it's not spectroscopy. It's a broadband point. With James Webb, we'll be able to actually trace out that feature in great detail, and you can do a lot of exciting science with that. So that's one very exciting thing on my sort of bucket list to look for in the coming year. TRAPPIST, I think everybody's excited about TRAPPIST. It's whenever somebody says the word habitable, no, goosebumps rise, right? But whether or not the planets are habitable, I don't know. But James Webb will be able to tell us whether or not the habitable zone planets in that system are indeed have atmospheres or water rich. So I think that will be a huge, impactful result in the next year. So definitely look out for that. That will be on the news. Whatever happens with TRAPPIST will be on the news. It's that important. Other than that, there are some large proposals for the first year. They're looking at all sorts of a wide range of planets. So instead of just looking at individual, particularly amenable systems, there are some sort of survey-like observations that are going to focus on a wide range of masses, wide range of temperatures and radii. So this will really get at more broad questions of diversity, trends within the exoplanet menagerie, and all sorts of that, all sort of more kind of basic questions about exoplanet atmospheric information. Yeah, and I'm also interested in solar system science. I do also actively research in asteroids, particularly the ones in the outer solar system, like type of objects. And during the first year, there are going to be a lot of survey observations of these objects. And there's a lot of interplay between solar system and exoplanet science. There will never be an exoplanet system that we know as well as our own solar system. So, insofar as we have the most intimate knowledge possible with our own solar system, we can ask questions about how representative is the solar system on the galaxy-wide scale, and whether or not there are certain aspects of our solar system that can inform the interpretation of exoplanet systems. So I think with James Webb having strengths in both solar system and exoplanet science, we're going to see a lot more synergy between those two communities. And I'm looking forward to that because I'm very much playing for both teams, so to speak. So,
are there any hyperbolic objects selected in the first year?
Sorry?
Are there any other hyperbolic objects selected to observe in the first year?
Did you say types?
Kuiper belts.
Oh, Kuiper belt, yes. So as part of the guaranteed time observations, there are about a dozen Kuiper belt objects that will be observed. And then there's also another program as part of the general observer. So these are competitively proposed programs in the first year. There's a large proposal that will look at like several dozen, like 30 or 40. So it's going to be, the floodgates are open for Kuiper belt science. Comets as well. Comets, there's going to be opportunities to look at comets as they get closer to Earth. And we will have, so comets are basically Kuiper belt objects that are fortuitously brought in very close to the Earth. So by looking at comets in great detail, we get an unprecedented view of what a Kuiper belt object could be like. So there are several comets that will be observed in in unprecedented detail, really, in the first year.
I'm excited for you, and it's good you're young because you're going to be up to your eyelashes in data, and you may be retired before you get through it all.
Yeah, well, yeah. I mean, the lifetime of this telescope, initially it was not going to be more than a decade. I think I actually don't off the top of my head what the initial estimates for the lifetime was, but by virtue of the better than expected insertion of James Webb into its parking orbit, the amount of fuel it needs to use to maintain the orbit is less than projected. So the lifetime has been extended significantly just by virtue of its near perfect, trajectory. So, certainly for the next decade, James Webb will be the workhorse chugging along.
With its orbit locked in there, is it possible to visualize it through an amateur telescope to actually see if you knew the coordinates of where it was, to actually see it because of its solar shield?
Yeah. So I don't actually know off the top of my head if anybody has done it yet, but it should be maybe not with a backyard telescope, but certainly with even a small astronomical telescope, a meter class telescope, would be easy to see. Yeah, I'm actually curious to see whether a backyard telescope can see it. It's in a part of the sky where it's perfect for, it's right near the middle of the night. It should be up overhead. So, yeah.
Wonderful. We're excited as you are.
Yeah.
Any other questions? All right. Wow. First of all, this is all very preliminary because this thing just got into orbit, and we're catching it right as it got out there. Now we have to check back with you in about a year.
Yeah.
All of this stuff and getting your take on the data, because I think it's really interesting how little we have and how much we realize we can get with the James Webb Space Telescope.
Yeah. Awesome. No, certainly throughout the first year, there's going to be a lot of science papers, a lot of nature papers on, first of their kind science, not just in exoplanets, but in all fields of astronomy, there's going to be, basically field changing results. On the exoplanet side, we're looking at the very first detailed transmission spectrum will be spectacular. Will be really an eye opener for the whole community. Not just the pretty pictures. The pretty pictures are great, but sort of the results are something that can really change our understanding of a lot of things. So So yeah, not even, you don't have to even wait a year. Like within the next months, there's going to be big results. Yeah.
I thank you greatly for your explanation of how the near infrared is much more data can be brought forth than instead of visual. That's very important to know and very helpful for us to know why it's working in the infrared.
Yeah. Yeah, I mean, there's another reason, there's kind of a technical reason also why it's mostly focused on the infrared, and that's actually the advancement on the ground-based side. We can see the whole visible, and it's called visible for a reason, right? We see the visible very clearly from the ground, and you can build an arbitrarily large telescope on the ground without worrying about the costs of sending it to space. So, sort of from a technical logistical aspect, the characterization of the infrared was driven by the fact that you have to go to space for that. Whereas on the ground, there's already 30-meter class telescopes being proposed and built in the next decade. So, you can't send a 30-meter telescope to space, at least not yet. So the decision to avoid to completely avoid the visible really was driven by that. If you don't have something in space, you can get it from the ground, perhaps even better than in space in the visible.
Well, that is awesome. I want to thank you very, very much for talking us through a few things that have happened and a few things that we'll see with the James Webb Space Telescope. Oh my goodness. First of all, no, I have a lot to get into, but I'll have to look a few things up first. Ian Wong, thank you so much for joining us this evening.
Yeah, thanks for having me.
Yeah, we are thankful, so thankful to have you here with us. And geez, I can't imagine what we'll see. And of course, the pretty pictures that come along with it. The data is what I'm thinking about. So again, thanks for joining us this evening, and please keep us in the loop. If you want to share, I guess you'll be publishing at some point about this, I imagine.
Yeah.
We'll be looking forward to that. I'll keep my eyes out, but I'll go ahead and share anything I find with the club here, and feel free to send anything my way.
Yeah, and if anybody's interested in following up on any of the information I talked about, you can send me an email. Elon, if you want to share my email, feel free to. I'm always open ears through email. So yeah, if you have any questions, I can give more detailed answers there.
Sure.
Via text.
And would you just read off your email if you don't mind?
Yeah, so it's Ian.Wong@nasa.gov.
At nasa.gov.
Yeah, so first name dot last name @nasa.gov. Easy. So, yeah.
Awesome. Well, once again, thanks for joining us this evening. It leaves me inspired. So thank you again, and looking forward to the good work that will come out of this, because it took a lot to get James Webb out there. We were all sort of on edge after the delay, after the events of getting it into space, but now we have some good science on the way. So excited to hear about it, excited to have you with us, and excited to have you back at some point, because we'll have some things to talk about.
Yeah.
All right. Well, once again, yeah, thanks for joining us. And with that, this concludes our August meeting of the Berks Astronomy Club. Thanks for joining.
Bye.